Okay. Thank you everyone for joining. My name is Bianca Chakamp. I'm the program coordinator from Oregon Mesa. Today, we're joined by PAE engineers for our first session of Career Week. We're hosting Career Week from today, Monday, March 7th, until Thursday, March 10th, each day at 5 p.m. Oregon Mesa, for those of you who don't know, is a program located in Portland State University. However, our programming is for middle school and high school students. I know that we've invited some of our PSU undergrads to this career talk because we felt that the topics today would be relevant for our undergraduate engineering students as well. This session is being recorded. Oregon Mesa uploads all of our virtual events to our YouTube channel. Audience video and audio features are off just to facilitate the panel. Please use the Q&A buttons to submit questions. You can upvote for your favorite questions there. Use the chat for general conversation. Do not share personal information like email or phone number in the chat, especially if you are a minor. And we will remove people who post inappropriate content in the chat and the Q&A. Portland State University is located in the heart of downtown Portland, Oregon, in Multnomah County. We honor the indigenous people whose traditional and ancestral homelands we stand on, the Multnomah, Cathlamet, Clackamas, Tumwater, Watlala bands of the Chinook, the Tualatin Kalapaya, and many other indigenous nations of the Columbia River. It is important to acknowledge the ancestors of this place and to recognize that we are here because of the sacrifices forced upon them. In remembering these communities, we honor their legacy, their lives, and their descendants. So today we're joined by PAE engineers. You'll be hearing from 6 speakers via a pre-recorded video. We'll be joined by Abby and Ruan at the end for a live Q&A session. At this time, I'll be turning the screen over to Abby and she'll be sharing with you.
Hi, everyone. Thanks for coming today. Give me just a moment while I get the video pulled up. Did have it close on me, which is unfortunate. So it's just going to be a second.
Thank you for your patience, everyone.
Thank you. All right, I'm going to be sharing my screen. Let me know when you guys see the screen.
Yes, we can see.
You can see it. All right. Let's see if I can turn off my video and mute myself. Please let me know if you can't hear the audio when I mute myself. I just don't want you guys to hear me in the background. Here we go.
All right, well, welcome everyone to our presentation about the PAE Living Building. We're going to be here to tell you a little bit about a project that we just got done with and about the team that it took to get this project to the finish line. You got on the call here, you got a bunch of engineers and architects that all had different parts to play in in this project and other projects that we work on. And yeah, so we're really happy to tell you a little bit about it. The images you're seeing here are actually from the project, and this is our new headquarters that we just got done with. It's in downtown Portland. You can see it if you come downtown and walk down to the Skidmore Fountain in Old Town Portland, and just head south a couple of blocks. We're at First and Pine.
Hi guys, I'll start with our introductions. My name's Abby. I'm a mechanical engineer at PAE.
I'm Gustavo Vela Moreno, also a mechanical engineer at PAE.
I'm Jacob Page. I'm an electrical engineer at PAE.
I'm Mark Bruni, I'm a mechanical engineer at PAE.
And I'm Sarah Cowan. I'm the Creative Services Manager here at PAE, and I'm really excited to be here.
Right. Well, I will go through and just kind of do a little bit of introduction about PAE and about the work that we do, and then we're going to pass it on, and you'll hear from everybody on the call here a little bit about some of the things that we're really excited about with our project, and what it takes as an engineer to put something like this together. So yeah, the agenda-wise, we're going to learn a little bit about architecture, engineering, the construction industry. What some of the roles are, a little bit about energy and energy flows and electricity and why we use electricity in buildings, and then the nitty-gritty on some of the systems that we actually have of how we heat and cool buildings, how we get fresh air into them, how we use water in them, and how we can conserve those resources actually. And conservation is something that's really important. We all know that there's a lot of challenges in the environment right now, and we can do it different. We can do it better. And in some ways, there's a lot of things that people are worried about right now, but it's also a really exciting time because we're at this point in history right now where we can actually change the world and we can do things differently. And and that's what I think a lot of the engineers that we have here at PAE, it's something that really drives us. We are here to make the world a better place, and we do it through designing buildings. We design some of the highest performing, lowest energy using, lowest water using buildings in the world. It's actually, the mission of PAE. We're in business. We're a business. You can come and work for us someday. And our mission is to help solve the planet's energy and water challenges. And like I said, we do it through designing these super high performing buildings. And this is a picture of the project that we're going to talk to you about today. Like I said, in Old Town Portland here, it's a 5-story office building. It's where actually our office is. And it's designed to be what's called a living building. And I think Gustavo will tell you a little bit about what a living building actually is. It's a really, really unique thing. There's fewer than 100 living buildings in the entire world. See here, so buildings, as far as the environment goes, are a really important piece because they use about half of the energy that that goes out into the world gets used actually in buildings, for turning on the lights, for using computers in buildings, for keeping them warm, cool, ventilated. And then you can kind of see where the other halves go is about another half or another quarter to industry to sort of build things, and then another quarter for transportation. And when you actually look at greenhouse gas emissions, the things that drive things like global warming, even more of that ends up in the buildings actually. So it's a really, really important part of the pie that we have to solve to get things back on the track that we want them to be on. And just one final slide about PAE. So like I said, we're in business to really help try and solve some of these environmental challenges. And we call ourselves is a triple bottom line company. So, a business is in business usually for profit, which is one thing, and that drives the business. It's the, the oxygen, so to speak, for business. Living things are not around just to breathe, but they have to breathe in order to be around. So that's kind of the profit side of the business. And then for us on the mission side, what really drives us is people and planet. So we call it a triple bottom line company: people, profit, and planet. And if we can get all those three things, that's when we're feeling like we're really succeeding. So with that, I will pass it on. And I think I forget who's talking next.
I am.
All right, Jacob can tell you a little bit about what it is to be an engineer.
Yeah, so at PAE, as you see on the slide, we hire mechanical engineers, electrical engineers, like myself, fire protection engineers, plumbing engineers, technology designers, and lighting designers. And while all 6 of those are crucial to the functioning of a building, the mechanical, electrical, and plumbing engineers in the Portland Living Building really got to shine in some of the solutions that we designed to solve at least our building's energy and water challenges. And so, let's see if the clicking works. There we go. So exactly what we do at PAE as engineers and designers is we research and analyze problems, be they presented by the client for something that they want or presented by the planet, and how best we can design a plumbing system to use the least water it can, or designing a solar array on the building such that it can save the most electricity. We communicate with clients, be they the architect or the owner of the building, and we also communicate with the contractors that are the ones that are actually building the building. And we design these systems, as it says, creatively, in order to make everything as efficient as it can be, as easy as it can be to construct for the contractors, and as aesthetically pleasing for the owners that are actually going to be occupying the building or leasing it. We also have to ensure public safety through emergency systems in the building for emergency electrical power and lighting, or the fire protection in the worst case scenario of the building that we have designed catching on fire, as well as adverse weather events or environmental factors like the smoke from the wildfires that Oregon's seen the last couple of years. We also have to meet client expectations for the design of their building, desires or requirements from them. We have to learn from our failures, hopefully, and learn from our successes and what worked, and use that data to keep improving when the same client asks us to do another project from them, hopefully. And through that method, to that point, we use the scientific method in order to get from point A to point B in a project. We research different products, different processes that we can use for a building. We research past designs that we've done and designs that others have done. We identify the problems that research can apply to, and when we really get to shine, we design a new solution to a problem that is interesting, and we'll talk about a lot of the new solutions we've designed for Portland's Living Building later in the presentation. And then once the project's done, through data that we can collect from a building and elsewise, we reflect on it, we see what we can do better, and then we test different solutions in the meantime in between projects to try out on the next one. And then we repeat the process ad infinitum. And then there we go. And with all that, as far as like we design buildings, we design the building that we are occupying. I'm sitting in it right now. We have to factor in how comfortable is it inside, how hot or how cold we want it to be, and how to get it there. We have to design and think about where the waste of a living building goes and how to capture that. We have to figure out how to get the water from the city, or in the living building's case, it's cistern, to the sink. We have to consider, what happens if the building catches on fire, as I said before, and we have to figure out and coordinate with the electrical utility how to get electricity from the power plant to the outlet that your laptop is charged into, and the speakers in conference rooms. As far as what else we need to think about, I think that's where Sarah comes in.
Jacob. So with all of those questions, great questions that we have to think about through the design, really it comes to the built environment professionals as a team. Who are these built environment professionals? It's architects, it's contractors, it's engineers, and consultants. And there are many types of engineers. For instance, as you've met with the team. But before we get into that, let's talk about a little bit about the process. And when you have a new project, usually it starts with the owner. You know, they decide that they made a decision, they have a piece of land and they want to build a built project. And so what they do is they kind of pull in an architect, bring in an architect on board to kind of help create the vision of what this building is going to look like. The architect also brings in the engineers, which is our team, to help design the systems that go into that building, help develop that function. As the engineers develop the design and work with consultants and whatnot, and once the design is finalized, then we kind of hand it off to a contractor who then facilitates the construction of the project. And we all kind of work seamlessly with one another to ensure that the project is built to how we envisioned it. Here's a great picture of our team for the Pae Living Building. We're standing in basically the basin of our cistern when it was first starting to be constructed. So it's just a great representation of how we can work together to build an amazing building. So who does what? The architect, as you probably already know, they help design the look and the feel and the form of a building and all its interiors, like thinking about the arrangement and all the materials that goes into it. The landscape architect is essentially like an architect, but more on the outdoor side of things. They help design the look and feel and form of all the outdoor spaces, including the plants and the trees and all the hardscapes and pedestrian places that could range from different levels of scale. There's also structural engineers who really think about the skeleton of a building. What's the load-bearing system? And then, of course, you have all of our MAPTL consultants, which stands for mechanical, electrical, plumbing, technology, and lighting. Again, they help design all the systems that are inside. And so specifically talking about all the different engineers and designers, what do they really focus on? Well, you have your mechanical engineers that really look at the quality of the indoor environments, the air, thinking about the comfort level in terms of temperature, with heating and cooling. You have the energy modeler who thinks about the energy flow that comes into and out of the building. A plumbing engineer thinks about how the transportation of the liquids into and out of the building. Think about the waste. Fire protection also thinks about the flow of water, but specifically more for safety with fire sprinkler systems. Your electrical engineer, they think about the supply and distribution of electricity. How do we get the power to the things that we need for a building to function? We have fire alarm designers who, again, thinks about the system of detecting if there's a presence of a fire. How does that work? And then the technology, thinking about the data and communication systems like your Wi-Fi, your audio and visual, and your security systems. And then lastly, we have lighting designers, how humans perceive and interact with the architecture through thinking of principles of lighting aspects. These are all the different types of designers and engineers that we have on board at PAE, and it's really a great team to collaborate with. So engineers design. So you have your design team. So talking about who designs the systems, but who really builds it? Well, the architecture. Think about the architecture, it's the general contractor. For mechanical systems, you have a mechanical contractor, plumbing systems, plumbing contractor, which is like possibly the plumber, as you may be more familiar with. Electrical systems, lighting designs is the electrical contractor, which would be an electrician. So those hand in hand, you have the people that really design the systems and the people who go in and install it. So from design to construction, there is a level of process. You know, how do we get to that end product? Well, words are not enough to give an instructions. Kind of like when you get an item from the store and then you have to piece it together. And you usually have an instruction manual. The same thing with a building. You need a set of drawings, a set of specifications and details to really help guide the contractors who are going to go in and build the actual project. So from then you would have like plans and drawings, blueprints, which we call blueprints. It could be plans that are more of like 2D representation, which means it could be like section views of plans or an actual floor plan, or it can also be three-dimensional. So more of the three-dimensional model, getting a more overview of what the actual building will look like from a holistic view. But we don't actually draw by hand much anymore. I mean, I remember back in my days when I used to be a landscape architect. I remember actually hand drawing on Mylar with T-square and all the special pens and everything. It was nice. But thankfully these days we have advanced technology with computers and all this wonderful software. And that's where a lot of our modelers come in. They help us really draw up all those great drawings. So from there, I'll kick it off to Gustavo.
Yes, thank you, Sarah. Well, I think a common trait I'd say of most engineers is we love to be challenged. We're kind of wired to solve problems. And in our industry with buildings, there's this living building challenge. And it really pushes us to think outside the box when it comes to the types of buildings that we're designing and how they relate to the environment and the communities that they're gonna exist in. So a few traits that are specific to this challenge include the building using all of the energy, the building producing all the energy that is going to be used in the building. Similarly with water, we want to collect all the water that will be used on site in the building. And that can be really challenging when you have a small footprint or a smaller roof. So then you want to focus on how you're using that water inside the building. So a few steps that we go through when we tackle on these challenges is from the get-go, we want to set aggressive goals because that forces you to think of maybe not traditional solutions, but it forces you to collaborate and think of innovative ways to meet those goals. We also want to be, aware of the climate challenges that we may face. It's not the same to design a building in California as it is to design it in Alaska. So we want to be aware of, the environment and the different conditions that the building will be exposed to. Also, good practices are to reduce the loads inside the building. So we want to make use of the most modern technology because it typically is going to be the most efficient. Similarly with the systems, we want to select systems that are very efficient and appropriate for the project. And then once we've got these efficient systems in place, then we can start to look at renewables and sizing, the PV. So it is at that point that we can see how much PV we need, if we have enough area on the roof to accommodate for that system. And then ultimately we want to see how we perform. So like that's the ultimate step, is like kind of like when you take a quiz or a test, you're always eager to see how you scored. And the same with us. Once the building is built, we want to see how good we did of a job in designing it. So next, I will pass it on to Abby.
Thanks, Gustavo. So hi, I'm Abby. We're going to talk about just some basic energy terminology we're going to use in the rest of these slides. We've been kind of throwing around words before. So simple energy basics. You may have kind of heard about this in your science classes, maybe physics, life sciences, but when we talk about different forms of energy, you know, there's mechanical, there's thermal, there's electromagnetic, electrical energy, there's chemical, and there's nuclear energy. For the purposes of what we work with, a lot of times mechanical engineers are working in our discipline. We're working a lot of times with thermal energy. So when we talk about heating and cooling a building, we're talking in terms of thermal energy. When Jacob talks about electrical systems, he's talking about electrical forms of energy. So just making sure we're all on the same page here, as far as we're not talking about, you know, gravity when we talk about energy. We're talking about thermal, electrical forms of energy. A really good acronym that I learned when I was in school was MELTS. It's a good way to think about the different forms of energy, and it's a fun little way to kind of separate them in your mind. We also do talk about sound energy when we're designing a system, because when you have a fan that's running really loudly, you're going to try and mitigate that sound energy and make sure that you can hear your teacher talking when you're in class, and you're not just hearing like a buzz in the background from the mechanical systems that are running around trying to cool the building or heat it. So taking these themes of energy and moving forward, Gustavo and Mark mentioned the Living Building Challenge is about taking your resources that are on site. So in the little square of our building in Portland, we're only allowed to use the energy produced from solar from rooftops. So you don't want to just throw solar panels on the roof and say, yeah, that'll probably work. Like, that's enough. When we do these kinds of projects, we analyze, we calculate, we run many different scenarios to say, okay, how much energy do we think each part of this building is going to use? And what does that mean in terms of number of solar panels and efficiency of those solar panels? Can we get away with residential grade efficiencies? Do we need to do something better? And then also the size of the battery for the building. So if you guys remember, like Tesla vehicles, if you've ever heard of a power wall, that's basically just a big battery that's on the wall of your garage. So we have to do what's called energy modeling to determine how much energy we need to store, how much solar we need, and what kind of equipment we can use in the building to really reduce our loads. So this is an example of kind of the different places that energy goes in a normal building. So we're going to call that like a good building, which is the code minimum. That term we throw around a lot in our industry, but it is just a basic building. So a lot of it goes to lighting, a lot goes to heating and cooling the building. Some goes to equipment, which we call plug loads. And some goes to heating the water that we use, like say taking a shower. In the building that we're building, or that we built, we have significantly reduced energy loads because we're limited by the amount of solar panels we have on our roof. So you can see there's a big difference between these two numbers. It's a metric we use to measure the amount of energy a building is going to consume. But this practice of figuring out how much energy it's going to use is called energy modeling. And that's a role of an energy engineer at PAE, kind of does that analysis and works with software and the other disciplines to figure out how much energy we're going to use. So you simulate the building in the environment it resides in, and we kind of look at like the angles of the sun going over the building, the orientation of the building, how many windows are on each facade, and that's how we figure out the energy that the building is going to use. And it is a really big tool that we use in reaching sustainability goals, and also running different scenarios to see if they're going to be cost effective and if they make sense for the client. All right, I think I'm going to hand this over to Jacob to talk about electricity and renewables.
And so as you were discussing at the end of the energy modeling section, a big portion of a building is how to provide electricity through it, to it. And with the living building, especially, as much as we can get from renewable sources was a big focus of ours. And so typical sources of electricity in the United States, at the very least, include fossil fuel power plants, which are at least my least favorite, solar panels, which are probably the most popular that most people know about, wind turbines that you can find in abundance in the Columbia Gorge in Northeast Oregon, hydroelectric dams or water power, as the slide says, kinetic, which the Bonneville Dam on the Columbia is also a great example. And then geothermal power, which is normally a steam turbine that's heated by the Earth's excess heat. And my alma mater, OIT Klamath Falls, has a lot of their electricity and heating comes from the geothermal sources around their campus and underneath the ground under them. And so this generated electricity that comes from all these different sources flows through the national electric grid. And sort of visible examples you might see of that are, as the photo shows, power lines running through the country on those giant towers, or local substations, which will be, they'll have all that equipment that you'll see and not necessarily be able to identify, and looks kind of menacing behind a chain link fence with a bunch of gravel around it. And then down to the local distribution transformers that you'll see, kind of a trash can sized either square or cylinder on a telephone pole, or a green box on the ground near in the neighborhoods if your neighborhood's power is primarily underground. But as I said, one of the most well-known sources of energy is solar power. And so solar arrays, harnessing the sun's different wavelengths of energy, turns that into electrons through the silicon. So each of those solar panels, if you can see, each rectangle is comprised of a bunch of different tiny squares. And each of those squares uses what we call silicon semiconductors to turn that wavelength into electrical current. And with how many squares per each of those rectangles, it takes a lot of solar cells to make up an entire, what we call a photovoltaic array, or a solar array. The term is interchangeable. Private homes have a lot of these on their roofs to power their cars, charge their electric cars, or to offset the electrical load of their house. And businesses like the Living Building use it to do the same, but also have the opportunity to send that electricity back to the grid in higher amounts than a normal house does. And this slide here is actually a representation of our living building. This is a side view of it, and you'll see at the top we have our solar panels in an alternating sort of angle on the roof, catching the sun. And that was actually a pretty interesting design that we came up with that for our building suited it best. And just below that on the 5th floor is represented the inverters, because solar panels produce what's called direct current, DC electricity. And buildings and the grid, for the most part, uses AC, or alternating current electricity. So the inverters change it from DC to AC and send it down to our 1st floor electrical room, where you'll see the microgrid control rack and the battery system to the right of it, the BESS. And then along the very bottom on the left is the different equipment that we have that will send our electricity at controlled times and in controlled circumstances back to Portland's Portland General Electric grid. And then this photo, as I said, is of our actual roof, with the alternating angled design of our solar panels. And really, this roof is a lot more dense in solar panels than most buildings will ever be, because the efficient insulation of the building and other factors reduced the rooftop equipment so much that it's what is that, 9 pieces of equipment are essentially all that there is on the roof, and the rest of it's available to the solar panels with some room for a couple other things.
All right, thanks, Jacob. So I am going to be talking about heating, ventilation, and air conditioning, which we call HVAC. So the basis of what we do is deal with the indoor comfort of a building. So what are factors that affect indoor comfort in a building? Well, a lot of times you just think about temperature, but you also need to think about the moisture level in the air. So that's called humidity. You also have to think about how many clothes people are wearing. So in the summer, people are going to dress a little bit different than in the winter when they're wearing their puffy jackets to class or to meetings. You also have to think about the airspeed. So if you've seen like big ceiling fans, that can affect the thermal comfort if you have like wind hitting your face. Also think about the temperature of your surroundings. So that's called like a radiant effect. So if you're sitting next to a big window like behind me, if you're sitting next to that and that window is really cold, like you're going to feel pretty cold sitting next to it. If you're doing homework like this guy is, he might be feeling hot because that window's hot. You also think about the air quality. So the contaminants that are in the air. I think Jacob talked about wildfire smoke. That's a component. And then COVID is also a component. A lot of what we do in the last year or two has been thinking about how we can address pandemic readiness in buildings. And then you also think about the activity level, like what is going on in the building? Is someone just sitting and reading like in a library, or is it a nurse station where people are running around and doing lots of different things at one time and they're very active? So these are all the kind of factors that influence indoor comfort that we think about when we design how much heating or cooling a space needs. And if we need to add moisture, remove moisture, etc. It's all very different depending on the climate you're in and depending on the factors inside. So ways that we as engineers can control thermal comfort. If you think about, if you're in an outdoor space, you're really not getting any refuge from the environment. So, but within a building, we're able to completely control that environment. So ways we do that, we can heat or cool the air and move air throughout the space, or you can heat or cool water and move that throughout the space to kind of suck heat or add heat to the space. Another thing you can do is heat a different substance. Some things like refrigerant are different substances that can carry heat, or in alternate areas, sometimes you can use like CO2 or ammonia, all these different kinds of fluids that you can use to heat or cool a space. So one of our questions earlier, we said, when it's hot or cold outside, what keeps it comfortable inside? So this is kind of a typical graph of the energy that you would see in a climate like maybe Oregon. So you have some heating that you need to do January through maybe April, but at the same time, from March to May, if you guys were in Portland a couple weeks ago, we had like a 65-degree day in February. So that's not necessarily normal, and that doesn't really mean that you need to heat a building at that time. So you have what's called like a shoulder season between maybe March to May, where you could have on any given day maybe heating needs or cooling needs. And then in the summer, you have time when you need to cool the building, and kind of a lot, like depending on the thermal factors that we talked about earlier. And then again, September to about November, you have a similar situation that we call a shoulder season. And then from that point on to December, you're heating your building. So these are all the what we would call heat loads or heat losses in a building. So if you think about a person gives off heat. Right now I'm presenting, I'm hot, so I'm probably giving off some heat to my surroundings. I'm looking right now at a big monitor, and that is a piece of equipment that is, maybe 100 watts. And that electrical energy that we talked about is getting lost to its environment. So it's adding heat to the environment. Right now I'm standing on a wood floor, and beneath that there's a foundation, and then there's soil. And soil temperature is usually around like 55 degrees. So the air in my house is maybe 68 right now. I'm going to be losing heat to that the soil that is colder than the thing next to it, which is the floor. Similarly with the walls behind me, there's exterior right there, so you're losing heat through the walls. A big thing that we think about as engineers is how we can insulate those walls to keep us from losing heat to the exterior, because Jacob worked so hard to get that energy to me. I don't want to just throw it out through like a very leaky wall or window. So we think a lot about these factors where we're losing heat and where it makes sense to improve that heat loss scenario. Similarly, lights are going to add heat to this environment, and solar load, so sunlight. It's not very sunny right now, but when you have sun through a window, like we saw that guy that was sitting next to the window, solar heat gain is a really big part of what we analyze as well. So at the living building, what we talked about earlier, we're moving a fluid to heat and cool the floors in our building. That's called radiant heating. So down here we have a bunch of pumps that have hot or cold water created through a system. And we pump that water to these floors at each floor and have radiant floors. So it's a really efficient way of heating and cooling a building. Different from a lot of other systems, but the reason we chose this is because it uses very little energy and it's pretty efficient. The other thing we're doing here is taking outside air, what we call ventilation air, and heating it a little bit, cooling it a little bit, but then just distributing it throughout so that all of our occupants have fresh air. So this is a different way to design the HVAC of a building. There's lots of different ways, but this is a pretty efficient and comfortable way to do this. So we'll talk about those radiant floors. This is what it looks like when they're installed. It's a bunch of flexible tubing that is coiled through the concrete or beneath the concrete slab. So you can see here a contractor is installing this tubing all around the floors, and it looks pretty cool. But the thing that I love the most is that dogs love it. We have a dog-friendly office building, and you'll just see dogs sprawled out all over the concrete floors because it feels so good to just touch. But it's really comfortable. So it's a great method to heat or cool a building that doesn't use a ton of energy. I think I'm going to pass it on to Gustavo to talk about the water cycle.
All right, thank you, Abby. So now that we've seen the electricity flow through the building, and we've talked about the HVAC system, let's talk a little bit about water and the different flows of water in the building. So for this part, I want to first focus on our resources, our water resources in the region. So Portland is known for its bridges, and the reason why we need bridges is because there is a big river dividing the city, and so there is a lot of water, and so water is a precious resource where we live. We do get a lot of rain, but it also means that we need to evaluate and take care of it and be conscious in the way we use it. So let's talk about how, water can be misused too. So a lot of older buildings tend to have a once through system with water. So what that means is that you only use water once and then you dispose of it. And so you send it out to the wastewater facility that will treat it and send it back to our water bodies. But the way we did this project is a little different. So here you see a section with the different plumbing fixtures. So you have lavatories or sinks, urinals and water closets or toilets. And so for this exercise, I want you all to just imagine you're a raindrop and you're gonna fall on our roof. And so you fall on our roof and you're gonna route down into that cistern. So we saw that picture of people standing in this like concrete box. So that's what the cistern is below the building. So once you're in that cistern, you're gonna go through a filtration and treatment system that will make the water quality as good enough to be able to be used for drinking, but also to wash your hands or take a shower. And that's what you see there, the distribution of the cold water and then the hot water through the hot water heating system. But then typically it's there that the water would be considered wastewater. But here we take that water back that's been used and it's now gray water. And we treat it again to be used for flushing. So now it's being used to flush the urinals and the really cool vacuum water closets that we have. So if you've been on a plane, you've experienced these. If you haven't, you need to come check them out because it's very different to what we're used to using, but very efficient, which is the main reason why we have them here. So it's a little bit of water and a lot of air and suction that takes place. And so then that water and the solids make it to these composting bins, which allow the chemical and biological processes to take place. And then we're able to recover nutrients and also use that compost for vegetation or, other purposes. And then we do have some like waste water in the end, but it's very little compared to what we would typically have. All right, and there you see the water goes back into vegetation. So it's a closed loop system. So this is the plumbing room or mechanical room, but it's this, all you see here is mostly plumbing. To the left, you see a lot of filtration happening. So this is when the rainwater comes down into the building to the cistern, and then out of the cistern, it needs to be treated to be able to be used for drinking and showers. So it goes through the UV lighting and the fine filtration, and then it gets pumped up to the building to be used by people. Towards the back there, you can kind of see the composters, and I think I have a better picture to show you what those look like on the next slide. And then here, kind of center there, you see the kind of creamish colored heat pump water heaters. Those are really cool because they use the waste heat from the electrical room to heat the water that will be used for showers or lavatories. So instead of rejecting and just having to cool those spaces, we cool them by extracting the heat out of the air and putting that into the domestic hot water. And these are the composter bins here. So this is where all the solids come once they've left the vacuum toilets, and the processes occur, and then take some time to get the compost to prime condition. But we have several of these composting bins to allow for those processes to take place. And as you can see, people are really into them there, checking those out. So now we'll get to see a really cool construction time lapse.
Maybe while this is going, I can just kind of give a little bit of a conclusion here too. So, I mean, this building produces all of its own power and treats all of its own water, captures water off the roof. It's literally not plugged in to the city water system. It treats it all, and that's where it comes from. All the waste that goes down the toilets, we're treating and capturing in those bins that Gustavo was talking about. It'll stay in there for about a year and a half, 2 years, and then it's going to come out. It's going to come out and it's going to look like soil. It won't stink. It's just going to be good dirt that you can actually grow things in. So, you know, we've kind of put the whole thing together, and we've thought about this building like an ecosystem where there's no such thing as waste anymore. And, you know, really as a living building, the intent is to, you know, that we've built a building that really acts just like, you know, like a tree might, that is growing on that site. It's gonna, you know, live within the energy budget that it has, of the energy that hits it from the sun. It's gonna live within the water budget that it has to, you know, from the rainfall that falls on the ground. And it's not gonna produce any waste. It's gonna be there, and, you know, and the ecosystem is better for it. And that's the way we're trying to think about living buildings. And you know, and lead by example. You know, we get to play with some really cool stuff every day and work with other people that, you know, the architects and the contractors that Sarah mentioned to make something like this a reality and really show the world that, you know, there's some different ways that we can do things, and you know, that can solve a lot of the problems that we have.
Well, thank you guys so much for attending. I hope that you guys were able to get a glimpse into what it's like to be an engineer or an architect to a certain degree, or a contractor, what kind of things you get to experience in a job at a firm like ours. I will say I was kind of recruited into this industry from a mechanical engineer who came into my environmental science class in high school, and I was like, that looks kind of cool. So that's why I pursued this, and it's really something that I love. And I feel really lucky to be able to truly mean that I love my job. That's not something a lot of people get to say. So if you guys are interested in a career in, you know, architecture, engineering, or construction, I can't encourage it enough. And if you guys have any questions, we are going to have a little Q&A panel after this. So yeah, stick around and think of some tough questions, and we'll do our best to answer them. But thank you guys for listening. We want to give a little round of applause to our presenters. Thank you guys for presenting and passing your knowledge on to our future engineers and architects. So thanks, guys.
Everyone.
Bye.
All right, thanks everyone.
Yeah, thank you everyone for listening. So Abby and Ruan are here for the Q&A. If you have questions, please submit them to the Q&A. There's a button at the bottom of your screen, and you can submit them there. You can also upvote questions that are submitted. And then I will first read out the questions to the speakers, and then they will answer if they choose to. They'll have the opportunity to answer every question, and we'll do our best to get to as many questions as possible. So please submit them at the Q&A button. Questions should go in the Q&A, conversation goes in the chat. Thank you very much. I'm going to just stop sharing so that we can see you all a little bit clearer. So Abby and Ruan, I guess what is the number one thing that you'd like Mesa students to know about what's available for them to see at PAE if they wanted to come in for a visit, or you know, see you all again at some other Mesa event? Where can they find you?
So we are offering tours of our living building. We are kind of open to the public. You have to arrange a tour with our office, but you could come in and get to see some of the really cool kind of groundbreaking systems that we have in our building. So we've got some very interesting mechanical, electrical, and plumbing designs. So that is definitely something to come in and see. And then we do offer internships to college students. So we've got all of those available on our website. If you're interested in applying, I can send a link to that in the chat. What do you think, Ruan? You got anything else?
Yeah, yeah. We also do offer job shadows for K-12, K through 12 students. So if you're interested in that, you know, you guys can email through Bianca, or you can email Abby or myself directly, and we can set up some short, you know, half day or whatever job shadows at the office, so you can get some experience hanging out in a professional environment.
Yeah.
All right. If you all would like to ask any questions, now is the time. If not, since we're at 6 o'clock, I might allow our speakers to go. I did have a couple of Mesa announcements, but any more questions? Going once, going twice. Okay, I'm going to screen share again just to go through the last Mesa announcements for now.
Thanks, guys.
And let's see. So we are hosting Career Week all week. Each session is going to be recorded and added to our YouTube channel. You can register at the links below or sign up at tinyurl.com/Mesa Career Week 22. We're having family nights, and Mesa students will be getting some emails about this from their regional coordinators, but all of the information is here. And we'll post this on our student website, YouTube channel, etc. And Invention Bootcamp is hosted at PSU. It's a 4-week Invention engineering camp held at Portland State University. It's from July 5th to July 29th. The deadline has been extended for Mesa students until Sunday, March 20th. Please submit. It is completely free for students, and they will help you with transportation if needed. Thank you. Make sure to visit Mesa Every Day, which is everyday.oregonmesa.org. That's our student website to find out more about our career visits and upcoming Mesa events. If you have questions, email us at ormesa@pdx.edu. Thank you, everyone. Okay, thank you. Have a good night. I'm going to end the session.